Hey, what's up? How are you doing, everyone? And today, welcome all of you, first of all. So, if you are here today, I really wanted to say hi in the chat section. And today is a very special day for all of us. You must be wondering why it's so special, why it's different. Because we have a great news for you. So, as you know, that you have registered for the system design. Uh, how to start system design for our interviews, and it is one of the most important topics out there. It is one of the most important topics in if you go for your interviews, and if you see like if you have to scale a system, and many of the interviews do have a part in it. But specifically our education of btech has doesn't have that required tinge to it. So you must now, we have someone special today in the house for you, and that someone special is going to teach you about system design. So Safir, I would like to welcome you to our live stream of Skilldojo.
Hey Prakash, thank you.
Thank you, Safir, for coming in. So, those of you who don't know Safir is a cloud architect, and he has formerly worked with companies like LinkedIn. And he is also the winner of 2 architecture battles, and he is really a grandmaster of system architecture. Safir, we are really glad to have you in our webinar today. And I'm personally very glad to have you in our webinar, Skilldojo webinar series, because this learning train is something which I always wanted to take, and it's truly a pleasure to have you. So it's over to you. I hope you share your screen. I'll just put your screen over it.
Give me a second. Yeah, started sharing. Can you see?
Yeah.
Great. So shall we begin?
Surely. So I'll take your leave, and it's you. And please, guys. Okay. Yes, people are saying hi. Hi, Atul. Hi, Saicharan. Let's start.
Cool. So let me start the presentation. All right. Can you see the presentation in the screen?
I guess it got removed from the share screen.
Oh,
Safir.
What happened? I don't know. System design, share. It's still not working. It was working earlier. Give me a second. All right. It looks like it's sharing now.
Yes, it's working now.
Awesome. Let me just start the presentation slideshow. Okay, if I start the slideshow, it's dropping off. I don't know why. I think, let me just, and let me share the entire screen. This is probably because of the way it's being shared. All right, present. Yeah, it looks like it's working. You can see the screen, right?
Yes, yes.
Cool. So I think we can start off. All right. All right, everyone. Thanks for joining today. A warm welcome to all of you. And thanks, Kiranza, for this opportunity to interact with you all and talk about system design, one of my favorite topics. And thanks a lot for your interest in system design. As Prakash was mentioning, there is a shortage of formal training on system design. But once you get into the industry, you are supposed to know it. So I hope this would be a starter for you. This is supposed to be a starter, like a system design 101. And while I have added a bunch of stuff for you to learn, it will be complete only when you have questions and we answer those questions and take it forward. So keep your questions ready and we will get to them at the end of this talk. All right, so before we begin, who am I? So my name is Safir. I've been a site reliability engineer and DevOps for the last 15 years. I have worked with companies like LinkedIn, Yahoo, Directory, etc. So infrastructure systems is kind of my passion, and that's why the topic of system design is close to my heart. So before we actually start the presentation, let us see what is covered here and what is not, because this is a 1 hour session and this is supposed to be an introduction session. So what we can cover here and what is not covered, let's look at them. So to begin with, the fundamental idea is to understand the relevance of system design, why it is required, where it is required, and what is the process of designing a system, right? And then once you understand that, you need to actually start designing, and once you have the process, you need to have some knowledge, fundamental knowledge, and building blocks to start building your system, right? So that is the second part that we are going to look into. And once we have established some of those fundamentals, then we are going to move on to a simple design problem to put all of them together. And in the course of this whole talk, there's going to be a lot of terms that you would see. Some of them you may not understand, some of them you are familiar with. Irrespective of that, there will be a lot of material that you can research once this session is over. And that is what is important. Remember that system design is not something that you can learn in a week or or just by jumping into a conf or reading a bunch of books. It takes time as you start building your knowledge on the systems, your fundamentals, and that is what is going to help you in your system design interviews and system design in general, right? So take this as a foundation and build on that. So what is not covered here? So we don't have a bunch of questions that you can try out or here. There's no question bank, but there's a bunch of questions out there if you want to try out, like YouTube, Google, wherever you search, you will see a bunch of questions. There is no shortage of questions. The shortage is about how you can systematically attack these problems and present a solution. So that is what we are going to look into. Distributed systems in designs, once you move from new college grad to a senior engineer or lead engineer, you would understand more about distributed systems. You will be in companies or handling softwares that works with distributed systems. That in itself is a huge topic. There are a lot of principles involved. There are a lot of different systems involved. That's not something that we can cover in the scope of this talk. But remember that that is something that you will encounter going forward. And once you have your fundamentals, you can start learning distributed systems slowly. And of course, we won't have enough time to deep dive into all the technologies that we touch upon here. But as I said again, you will have a lot of materials to research and understand. So to begin with, right, system design is part of software, right? Building a software, right? So to begin with, the initial or the starting question, how do you build a software? If you're fresh out of college, you would remember what you read about SDLC or the software development lifecycle, right? SDLC is essentially the process of designing, developing, and testing a software and getting into production, right? So roughly, so again, SDLC, while there's a bunch of things that we learn about it, the core is the stages or the phases in an SDLC, right? So some of the important phases are planning, requirement analysis, prototyping, development, testing, implementation, and maintenance. So if you look at them, right, planning is you are actually planning to implement some software system, and then you understand what is the requirements for that, analyze them, design them, and then you prototype them, create a mini version of the actual system that you want to build, and then you start developing the entire system, keep testing them, then you implement and roll them into production, and then you keep maintaining them, fixing bugs, adding more features, things like that. So this is a typical cycle of developing a software system. Now the process would vary a little bit here and there depending on which companies where you're working. The company culture might have an impact on that. There could be situations where you have very small software where you don't have to put a lot of process into place. So all these things would impact how you handle the SDLC, but essentially most of these components will be involved in small scale or large scale in your software design process. So this just just touching upon the theory of SDLC. There are a bunch of models, waterfall models, V-shaped model. All of this is essentially dealing with how you are handling the development process, right? That's all they are doing. Of course, you can check out all these things, but to be honest, these are not the fundamentals that you have to learn. This is just for it to set a background for what we are going to talk next, right? So agile is a methodology, software development methodology that is popular nowadays. It makes development faster compared to conventional SDLC process. So it uses Scrum, Sprint, Kanban, a lot of those methodologies. But irrespective of those methodologies, you have at the end of the day, you are developing a system, software system, right? So let's ask that question, what is system design? So system design is a process of designing the architecture of the infrastructure components on which the software system will be built, deployed, and maintained. So what does this mean? What is infrastructure, right? So you are developing a software which has to run on a computing system, right? It could be just one server sitting in in your basement. It could be something in your data center. It could be on the cloud, right? But there is a computing system, a bunch of networking systems, like a whole infrastructure, right? And is that good enough? No. There is going to be software components which will be running on those machines, which will talk to each other, and which will host your code. And your code will make use of this entire resources of softwares and hardware and all the computing systems, and run your application, right? So designing that infrastructure part of is what is usually referred to as system design. Now, in the whole SDLC, where does the system design fit in, right? So if you remember the previous phases we discussed about SDLC, there is a requirement analysis and planning in the beginning, right? So requirement analysis essentially what is the system, the software system that we are developing for? What are the features required? Where will it run? How many customers will be served by this software? What kind of data will be dealt by this software? All these things comes under the requirement gathering, analysis, and planning. So that is where most of the system design components would be part of these phases essentially. Okay. So irrespective of what software method or agile methodology or typical conventional SDLC process that you are following, there's always going to be a planning phase, and your system design is mostly going to be part of your planning phase. All right. But having said that, right, there is also situations once you start developing something, there is always a good chance that some parts of your system would change, or you will have to tweak it accordingly based on the changing requirements, or you will discover something is not going to work as intended, things like that. But it's mostly going to be part of the planning phase. So before we jump into these definitions, right, one word of caution. If you start researching about system design, software architecture, things like that, you will see a lot of definitions, a lot of wording, things like that, and it could be a bit daunting and confusing, right? I'm just using these definitions in my own terms so that you get foothold or understanding about the fundamentals. But beyond that, don't take it okay, what is system design versus software design, right? It's about understanding that segregation and the logic. That's all. Okay. So depending on how a company approaches their software development, right, some of the design and architecture terms would differ, right? So some of these definitions, right, it could be very loose definitions. Some people would use software architecture as a replacement term for system design. That could happen, right? Assume that you are in a small company, software system, everything is being designed and developed together, right? So depending on like a small software, the scope of your design would be very limited. There won't be a clear boundary about what is system, what is software, and things like that. But as you're if you're dealing with a huge software component or a software system, there is going to be certain boundaries. So I'm just going to look into those boundaries and talk about that. So software design, right, the way I would see it is software design is basically about conceptualizing the software modules that are required for running the application based on the business requirements. So let us say if you are going to design YouTube, right? What is the ask from the customers? What is that the business model? What we are trying to achieve here? Are we going to display ads? Are we going to what is the medium we are going to use it? It's going to be videos. So these are kind of like the business process. Now, when you conceptualize the software modules, you are actually talking more about the software that you are going to develop, not the systems, underlying systems. That comes after that, right? So that is where you conceptualize your software modules, right? And then you decide like okay, this module has to module X has to be integrated with Y, and at the same time it will be communicating parallelly with like system A or system B. So that is how like you decide the interfacing, right? And another important part is like identifying the data. What kind of data are we dealing with? Is it transient data that's passing through the system, or are we going to store this data, and are we going to convert this data into something else, right? And also like what kind of software languages, framework, what all things we would use. That also comes under software design. Now if you come to system design, right, determine the infrastructure components and services that will be required to support the software design. Now if you have to, let's say again come back to the YouTube analogy, right? There you would require like huge bunch of storage for like your videos. You would require a lot of computing processing for like converting videos into different formats. All of these are going to be your infrastructure components, but ultimately what is going to be those components is decided by your software design, right? In your software design, it says okay, I have video processing requirement that comes from the business, and I'm going to write a video conversion. Like if you are uploading one particular format of video, the system has to give 5 different formats of that video, and that is going to be a software module. And that module would require a bunch of computing and a bunch of storage. And I would use open source technology X and Y for doing this. I would also require like a huge amount of SSD data disk, or like fast gigabit Ethernet, those kind of things, right? So that is where the infrastructure pieces meets the software components. So again, defining interactions between the services, just like your modules interact, there's also like all these components interact behind the scenes, right? So that has to be decided. So again, based on the business requirement, you have to estimate the scale of the system. So a system that is going to be developed for like 100 users to use and like 1 million users worldwide, those are going to have like entirely different scaling requirements. So that is very important in the part of system design. So it's not just enough to have like all these systems in place and interconnect them. You need to make sure that those doesn't fail. Again, systems fail, and it's a guaranteed thing. So when I say we need to ensure system doesn't fail, what do I mean? You need to introduce additional safeguards and like additional copies of data or systems or whatever is required to counter and recover from that failure quickly without the customers getting impacted, right? So then the other one obviously is like identify. So when you are dealing with a large system, there's always a chance for like performance bottlenecks, right? It could be your network being choked, it could be your disk being choked, or it could be just like the way you have coded your application so that you cannot handle, let's say when your customers are 10,000, you can only handle 1,000 requests at a time. At a software level, there is a limitation. Again, that need to be identified, and those kind of bottlenecks need to be identified and fixed. So this is what comprises mostly system design. And again, between software and systems, there are like a lot of shared responsibilities, right? So both of these systems essentially depend on like the initial requirement analysis, because what the business wants, what is that we are going to develop, and what is our end goal is extremely important for both of them, right? So that is the foundation for like the whole design and planning process. So there is always going to be like a high level design which will be shared by both software and like the systems, and both of them would develop high level low level diagrams from those high level diagrams in a different way, right? And again, understanding data is important for both software design as well as system design. And then scale, we talked about scale, resilience, and failover, like how the systems could fail, while we could introduce failure safeguards in the system. The software should also be ready for that. Just because you brought up a new system to in place of your failed system doesn't mean that your software is ready to talk to that system. right? So that is why software, your software design and your system design has to be in harmony about it. So a bit of facts about the system design process, right? In the interviews, usually you are the only one designing the system, but in the real life, it is not like that. So it's always going to be a team effort. Different people will play various roles. Somebody, one or two people will be tasked with the initial design, probably that the senior folks in your team. That's always a probability, but everybody has a say, and and it evolves actually. So there will be an initial draft of a design, and then you pitch in your ideas. You point out the probable improvements, probable mistakes that could happen, and that process is what makes the system design better, and that will evolve into a better system, right? So while you lock the initial design phase and say, okay, this is my design, there is always a good chance that 5-10% of your system could keep changing by the time you develop and deliver the system, because there is always going to be unforeseen circumstances that could cause your design to change. So irrespective of what role you play, right? Did you take part in the initial design, or were you you joined later when you were actually developing the system? Irrespective of all your roles and what you did in the system, as long as you are part of a system, it's imperative that you understand the system fully. You understand why a certain decision was taken, why a certain design was chosen, and that is what will help you to support that system and develop or add features to the system. So now we are entering part the system design characteristics, and we are beginning with the system design, right? So some fundamental characteristics. This is not all, but these are some of the fundamental characteristics of a good system: scalability, availability, and fault tolerance. So let us look at scalability. So what is scalability? So it is the capability of a system to withstand the growing demand. Growing demand obviously is the demand from the customers, or whoever is the user of the system, and serve those requests as intended. So today you are serving 1,000 users with a good quality of responsiveness. Tomorrow, if there are 10,000 users, you should be able to withstand that, right, with the same quality, and that is called scalability. So a well-designed system can achieve scalability without compromising on performance, and that is the goal. And of course, there is there is always compromises or limits that you have to set for scalability. So today you are serving 10,000 customers. You should probably account for 20,000 customers if that is how your business expects to happen. But you don't engineer for a million requests if your current users are 10,000 users. So it all depends on your business, the situation, etc. Okay, but scalability has to be there without compromising on performance. So how do you scale, right? You have to benchmark the system. Once you have the design, or you started developing things, you should be able to benchmark the system and say, given my software's capacity and how I have deployed it on these computing systems, what is the capacity or the number of users it can withstand? So based on that, you have to benchmark and provision additional capacity if required, and you have to ensure that all the subsystems within the system that you designed can scale up when needed. So one way of scaling is adding load balancers, which can distribute loads across a bunch of a fleet of systems. You could also your data could also become a bottleneck at some point, in which case you can partition the data or distribute the data in whatever way you see fit. The next characteristic is availability. So availability is the probability that the system will work as required, when required, during a period of mission. So what is this period of mission, right? So see, the system design as a term and as a field of design, it didn't start with software. It started with industrial systems, right? So everything is a system, right? Anything that you engineer is a system, and it has to have all these characteristics, right? So let us say there's a satellite that has to go on a mission for 1 year or 1.5 years. For that system, engineering system, this 1.5 year is the period of mission. But in the case of softwares, most of the softwares that you develop are supposed to run indefinitely. So the way we calculate or look at availability Availability essentially is like a probability or like a percentage, right? So what we calculate is the availability for an year. That is the mission period for software systems usually. So the way you talk about like the availability is in percentages. So to give you an idea, right, a system that is available for 99.999 percentage, it's also called, like in the industry, it's also known as 5 nines, because there are 5 nines in the number. That means that the system is unavailable for a period of 5 minutes in 1 year. So this number is also called SLA, or service level agreement, right? So it guarantees the customers of a system that okay, this system is going to be up for an year, just 5 minutes short of 1 year, right? So if you are just saying 99% availability, you can calculate like calculate the time based on like 1 year period, and how much time it will be unavailable, and then think about like whether that will be an acceptable availability limit for your system. It won't be, honestly, but that is how you calculate. Okay. So to ensure the availability, so the systems has to incorporate what we call high availability principles. Okay. So in the design, when you have to look at high availability, the term that comes up always is single point of failures. So single point of failures is essentially like you have one computer running your software. What happens if that machine goes down? Your service is down. That is called a single point of failure, and this would happen to any computing component. It is not just about the number of machines, just one machine. As a software, let's say for your software to work, there are 5 machines working together, and by design, if 2 machines out of that goes down, your entire system collapses, even if the other 3 machines are running. That's also a single point of failure. So the single point of failure is determined by the characteristics of the system that you are designing, or the components of those systems. So you need to identify those single point of failures and fix them with like the HA technologies. So HA, or high availability for data. Let's say there are data replication, partitioning. Then in networking, there are like HA protocols that will help you to like switch traffic from one server, one computer to another. There are protocols which allows within software like find out like what is the next best machine that I can talk to. So all these things supports implementing availability. Now let us look at fault tolerance. So what is fault tolerance, right? See, the failure, any system would fail. That has to be unaccepted. Like if you are designing a system, you need to know that at some point the whole system or parts of the system will fail, right? So how do you fail proof these systems, right? You need to make each component of the entire software system fault tolerant. So that will enable the system to keep operating even when one or more components of the system fails. So when something fails, there is always another system that can take over and like function like nothing happened. That is from the customer's perspective, right? So how do you do fault tolerance? You introduce redundancy to all critical systems. So there's a single point of failure. You introduce redundancy over there. Data has to be replicated, and multiple copies of the same systems can be run in active mode. We'll talk about active mode in a bit. So if you look at fault tolerance, right, it would look like fault tolerance and high availability have similar goals, right? But a small distinction is like this, right? Fault tolerance has to ensure that even when a component fails, there is another copy of the service that should take over without any impact to the service, right? Even if the performance degrades, that's very critical. In the case of a high fault tolerance system, a small degradation in performance is acceptable as long as the service go through without the customer noticing a failure, right? In a highly available system, a single transaction can fail, but the next request should be still available and like performing. So to give you an example of to avoid the confusion, right? Let us look at an example, right? Assume there is a web service, right? A customer is requesting something from the web, and at some point when a customer is requesting something from this this website, the system, one of the systems serving the web server fails. Web service fails. At that point of time, there's a good chance that this particular customer who is sending a particular request would see an error instead of data. Could be a 5xx error from your web server. But the next customer or the same customer's next request would not fail. That is how like highly available systems work. Now, if it's a fault tolerant system, what happens is a system fails, the customer would notice a delay, but he won't get a response for let's say, usually he was getting a response in 5 seconds. Now he would probably get it in 10 seconds, but he ultimately gets a result. At the cost of performance, he or she gets a result back. So that is the idea of fault tolerance versus availability. So now we are looking at going to look at the building blocks of the system design. What constitutes system, right? When we are actually building a huge system with a bunch of components, we need to know essentially what are those components that will help you design a system, right? So those building blocks are of different types, right? There are principles, there are strategies that you use, and then of course you have to use all those strategies and principles on technologies and applications, so that you can build a system. This becomes your foundation knowledge to do a design. Irrespective of the problem, you need to know some of these building blocks, which is not tied to any particular problem, and understanding those building blocks is very much important for the whole system design. So let us look at some of the fundamental principles and technologies that are required for you. Okay. So the one that I'm listing here, right? It is not just specific to system design. It's about every engineer who is dealing with computing has to know most of these things, right? So networking, right? Understanding the fundamentals of TCP and IP stacks, how the routing works, how your DNS works, to the point of how you own a DNS, DNS server, or how you host a domain, all these things, or how your TCP works, what happens when your system fails halfway through a transaction. All these things are part of networking, and that is foundation, one of the foundations. And of course, we are dealing with WebRTC mostly here. When we are talking about system design, 90% of the time it is about something in the web, right? So web protocols like HTTP, HTTPS, how HTTP2 works, WebSockets. If you are doing real-time communication, WebRTC is important to know. And of course, security is foundational. So SSL and TLS, how they work, is important. Everything is an API now, so understanding REST APIs is very important. So again, that's about the software stacks, right? So also it's important to understand a lot of at least a bit about how the hardware and networking works. What is the difference? Let's say for example, what is the difference between a switch and a router? It's kind of foundational knowledge, right? Or how most of you probably would have seen, or at least some of you would have faced the question what happens when, and then comes a scenario. Most of the time it's the question that will be asked is what happens when you type www.google.com on your browser? What happens? Now you could go into a whole bunch of details about this question and talk about networking, routing, system calls, kernel, everything, right? So if you look at those questions, and of course you can get answer to these questions in the internet, but it will tell you that these are the things that is happening under the hood, and knowing these things at least to an extent helps you in understanding the problems and solving the problems. So then again, storage is important. So understanding basics of file system storage. There are storage protocols like NFS or remote storage, Samba, all those stuff. So understanding a little bit about that helps in again designing systems. Of course, fundamentals of operating system, how the processes work, how the memory is managed. All those things are these are again foundational computer science knowledge that you need to know. So we are going to look at the actual building blocks. Again, this is not an exhaustive list. Please remember, these are some of the very fundamental building blocks of system design. There is a whole bunch of other things that we can talk about, but given the time constraint and given that this an introduction, I'm only including these many services. So let us look at the first one, load balancer. So what is a load balancer? It's a device that accepts a network traffic. It could be web traffic or some other application traffic, and distribute them to a fleet of servers that are sitting behind the load balancer. So what is the purpose of this? It ensures that there is a high availability and reliability of the service. So as long as the load balancer in itself is alive and working well, it can accept the traffic, then distribute it to a bunch of servers, based on some algorithm. So what happens with that? It shares the load equally between the machines, looks at how all the systems are loaded, and tries to balance them in the right way. So this is how you scale a web stack or any application stack for that matter. Okay, so traffic can be distributed using like very different load balancing algorithms. Some of the common algorithms are like round robin. So let's say traffic is coming from a user, send that the load balancer sends that request to server 1. You have like 3 servers. The next request comes, send to second server. The next request comes, send to the third server, and the fourth customer goes to the first server. So that is round robin. So then there is weighted round robin. Let's say you have two 32 GB machine and 164 GB machine. Obviously the 64 GB machine can take the double traffic, so it gets a weight of 2 when the other two machines gets a weight of 1. So that is called weighted round robin. Then there is least connections. If there are like one machine is getting very less request, that machine should get more requests. So if the load balancer is able to track that connections, it can send more traffic to that machine. So then there is least response time, depending on like how well the system responds. Yeah, the load balancer can send request to the most performing machine. Then there is a way to like hash the request, depending on like the request data or like the IP of the sender. All those things are like different protocols to or algorithms to be used for like choosing the right server to send traffic to. So this is a rough diagram of how the load balancer works, right? So you have all the customers here, your end users who would be connecting to your service through internet. So the load balancer could be a software load balancer or a hardware load balancer. So this is the age of cloud and cloud computing. So a lot many times when we talk about load balancer, you will only see a software entity that you can manage from the web, right? So that is probably a software load balance we are talking about. Then there is hardware equipments that you can put in your data centers, which can do this at protocol levels. So those are hardware load balancers. But irrespective of whatever load balancer you use, the principle is always the same. It receives the request from the customers or the clients, and then distribute them to a bunch of servers sitting behind the load balancer. So the benefit is obviously like there is reduced downtime. Let us look at like what happens when a single machine goes down, right? So you have like 10 machines sitting behind the load balancer. A machine goes down. The thing that load balancer does is it keeps doing a health check of each of the servers. It keeps sending a request to these servers to say, okay, are you alive? Can you serve my next request? So if a machine goes down or it doesn't work properly, the load balancer doesn't send any traffic to that. It considers that machine as unhealthy or like dead. So that way your customer don't see an error, because his request, instead of going to the 10th server, let's say it just goes back to like the first server or another server, based on the way load balancer works. Scalable, of course, like you could keep, so as long as the load balancer has the capacity, you can keep adding machines behind it. So that will help you like handle more requests. And of course the redundancy, just because if a machine goes down, either you can add a new machine, or even without the machine you can operate on a reduced capacity without issues. Flexibility of adding and removing machines is also very efficient in terms of computing. Now let us look at proxy. So this is a term I'm sure almost everybody would have heard about, right? So a proxy, by definition, is an intermediary server that sits between a client and a web server. So a proxy can do a bunch of things. Some of them are like filter the requests that are passing through the intermediary, or log them or transform those requests into something else, depending on like whether the request sent by the client or the response sent by the server. So there are two main types of proxies. So what we call as just proxy, or like is also called like the forward proxy. So it sits in front of a bunch of clients and forward the request to the internet, or let's say a web server in this case, right? So forward proxy essentially sits in the premise of a customer. Let's say your office, you are like 10 people sitting in an office, and there's a proxy installed by your IT team in your company. The intent of that is either to enforce some policies. Okay, you should not be visiting like job searching sites during your working hours. It's probably a policy. Or it could also be used for like implementing some security. You should not access like HTTP websites, only HTTPS secure websites. Or it could be just for like introducing caching and like speeding up your web browsing experience. But irrespective of that, it sits closer to the client and intercepts the request and sends them after filtering or doing the necessary transformation. Reverse proxy, it sits in front of a web server in the servers or the company's premises where the web server is sitting, right? And it intercepts the client request just like the forward proxy. It intercepts before it reaches the actual web server which serves your request, and then it can also intercept the response from the server that is going back to the client. Why would you need that? You can fine-tune the request and response. It could be altered for better performance. You could introduce zipping or other performance improving mechanisms. You could also implement security. So a lot of companies implement perimeter security or filtering at the end to avoid a lot of attacks using reverse proxies. So this is how the forward proxy looks. So this is your user sitting, and the forward proxy is just along with the customer, and then the traffic goes to the internet and reaches your servers. So origin servers is a term used for the servers that ultimately serves your request. There's a term that you would keep seeing in proxies, load balancers, content filtering, all those kind of stuff. So when somebody says origin server, that means that is the ultimate server which serves the content that you are supposed to get. Now if you go to reverse proxy, the role is reversed here, right? The client actually sends the request out to the internet, and when it reaches the perimeter of the let's say you are sending it to Google. When it reaches the perimeter of Google data center, reverse proxy is the first one to intercept that traffic, and then after the transformations that are required, it sends it to the origin server sitting behind the proxy, right? So in system design, we are more interested in reverse proxies, obviously, because they are sitting in the data centers or close to your system that you are going to design, and it adds a lot of value, right? So what are reverse proxies usually used for? Just like load balancer, reverse proxies can also do load balancing, but there are some caveats or additional systems that are required to for them to function properly. So it can also transform request and response, offloading SSL, compression, etc. So why is this required? Let's say you are enabling SSL in your web application. When your web application directly has to serve an SSL, that means that the encryption and decryption of that request, every request, has to be done by the application server, which is additional CPU usage for that machine. But if you have a proxy that doesn't do the application logic, but rather just intercept the SSL traffic, does the decryption and encryption and sends the traffic back and forth to the origin server, then you are offloading that work and freeing up the CPU of the application server by introducing a proxy. So that is offloading SSL. Same case with compression. You can zip. Zipping is a CPU intensive process, zipping and unzipping, which could be done by a different server, which a different proxy sitting in front of the application server. Security and content filtering. Let's say certain patterns of searches or certain pattern of attacks. There are modules that you can install along with the reverse proxy that can look at suspicious patterns and filter those requests before it reaches your application servers. So routing different URLs to different set of servers. So let us say your application has a customer endpoint as well as employee endpoint. So /customer could go into a bunch of different application servers, and /employee could go into a different set of application servers. That is URL mapping essentially. That could be done by a reverse proxy. Caching, again, we are going to see caching in a bit more detail, but caching in general is saving content so that it can be accessed faster. So all these things can be done by a proxy. Next, we are going to look into database. Excuse me. So again, database, I'm sure pretty much everybody is familiar with, right? It's a critical component of almost any systems. See, the database stores the data, right? And without the data, the web has nothing to deal with, right? Essentially, computing and web is all about processing data. So this is the cornerstone of your systems, whatever it is, right? So when we talk about database, there are two distinct types of databases. RDBMS is what we are going to be most familiar with, relational databases or SQL query based databases. All right, so this is the very fundamental, the very first database that you would learn in any computer science course or when you start working in software. The other flavor is NoSQL. NoSQL is not just one technology; it's an assorted set of technologies that can store different type of data sets, like key values, documents, relationships. A lot of data that doesn't fit into the conventional relations entity model of RDBMS. So if you look at RDBMS in detail, right? So relational databases defines the entity relationship in a data set. So it says, okay, they have columns and rows for each entry, and between those entries there are keys that would define keys that will define relationships between these entities, all those things, right? So relationships is the fundamental to the RDBMS, right? It's a relational database, and queries typically it's transactional in nature. If you might have learned about asset properties, right? So that is again very fundamental to RDBMS. Some of the example softwares are MySQL, PostgreSQL, Oracle, MS SQL, things like that. So RDBMS has very rigid schema. What is schema? Schema talks about what data type you have for a particular table, or what are the conditions, what are the relationships. All these things come into picture in a schema. And the schema in RDBMS are not flexible. You define them, it's very that relationships are very well enforced. Okay, so typically the way the contents works in RDBMS is tables with fixed rows and columns. Again, vertically scalable is a term that we will see in another slide, but that is one vertical that is one way of improving the performance or scaling the capacity of RDBMS. So NoSQL databases, right? It's as I said, it's an assorted set of technologies. So there are various data models that NoSQL can host. One is document store, that is usually a JSON document. There could be key value pairs. Then there are wide column databases which will have unlike RDBMS, there will be for each row there could be a different set of or different number of columns. So that is wide column. Then the the newest technology in NoSQL world is graph databases. Graph databases are the best for defining complex relationships. If you are building a social media clone, most probably you are going to build or use a graph database. So they will have nodes and edges just like your fundamental graph theory. Okay. So the way the DB is called, so in RDBMS it was SQL always, and it has a particular format. In the case of NoSQL, how the DB is queried varies based on what kind of data models, what kind of software you are using for querying that particular data store. Okay, the schema in NoSQL database are either flexible or there is no schema at all, right? And they are usually horizontally scalable. Again, we will come back to scalability in a bit. Caching, right? So you would have definitely again heard about this term, right? So cache is a high-speed data storage layer which stores a subset of data, typically transient in nature, so that the future requests for that data are served up faster than is possible by accessing the data's primary storage location. That's a lot of terms, but what is it actually saying? We are dealing with data here, and there are data that are used for a particular period of time. That's why it is transient in nature. And when you keep the data in a location that is faster accessible than the original your web server or storage wherever you have stored it, your performance overall improves. That is the intent of caching. So caching allows you to efficiently reuse previously retrieved or computed data. It could be just a static data or an image or a JS, or it could be some computed data that you store in an in-memory storage. So again, caching can happen at different stages of web application communication. I'm sure you all have cleared your web caches at some point in your web life. So that is one of the cases. Then there are services called content delivery networks or a proxy that can cache the contents of a website closer to the customer. Again, we will revisit the content delivery networks in a bit. So for a database, how you can cache it? So let us say you are retrieving some data from the database, and database queries are usually a bit expensive, and especially for a loaded heavily loaded RDBMS system. So what you can do, you introduce an additional cache where the data that doesn't change very frequently can be put. So the application will first query the cache, see if there is data, and if it is not there, it will go back to your database. So this is like the fundamental principle of caching, right? Let's say you have a client here, you have a the origin or like the end server from where you have to retrieve the data. Now let us say that it takes 100 milliseconds to fetch the data from your actual server. Now assume you introduced a server that sits closer to the client, and its only job is to cache some content that can be retrieved from the origin server. In that case, what happens? Instead of this red line here, client request some resource. Let us say that I'm logging into some website and they are retrieving my profile picture. All right. So the client request is from the origin server. Instead of origin, in the case of cache, the client requests my profile picture from the cache. What the cache do? It looks at its own storage to see whether my profile picture, which will definitely have a particular file name. It would look for that file. If it is not available, this is the first time my profile is being fetched. The cache service on behalf of the client will talk to the origin server and fetch that image and return it to the client. But the second time the client comes and asks the cache, hey, give me Safir's profile picture again, the cache will have it in its storage, and that cache will be returned. In this case, what happens? The first time fetch takes 50 milliseconds plus 50 milliseconds, but the second request onwards, it takes only 50 milliseconds. So that's obviously a performance gain. So this is a fundamental principle of web caching. Now we talked about content delivery networks earlier, right? Which can be a caching network, right? So let us look at what are the components here. There's an origin server, there is a CDN server, and then there is your end user. So this is the actual application server where your content resides. Let us take the same example of my profile picture, right? So my profile picture originally is here. I signed up for the Europe, this application, and the I uploaded my profile picture, which sits here. Now one of my client access this application from a remote continent, right? So if let's assume there is no CDN, this fellow has to, the request has to travel all the way across continent through internet and come to this server and fetch my profile, right? Now assume that there is a content delivery network. What happens is when there is my profile picture added into this application server, all these servers are notified. All these servers that are owned by the content delivery, it could be a company's content delivery, or there could be service providers like Akamai who gives you this service. They will know that, okay, there's a new file added to this system. Let us fetch that and keep it in all these servers across the globe. So that is a function of content delivery networks. They keep a copy of these images in their local servers. Now in this continent, for that particular server, CDN provider, there is a server which hosts my profile picture. So if I access it from here, or somebody else access my picture from here, he doesn't have to travel cross continent to this server. His request is immediately answered from this server, which improves the performance. So if you look at the computing way, right, a cross continent traffic could cost anywhere between 250 milliseconds to 500 milliseconds. But in the same continent, so this is pretty much in India, I believe. So if it's in India and you are sitting in India, it's probably 5 to 10 milliseconds. So that is the improvement that CDNs adds. If you have a worldwide customer, it's imperative that you add a content delivery network in front of your application service as a caching layer. So database caching we talked about, right? So let us say you have an application. So the application would usually talk to the database to fetch some data. Now usually if there's no cache, you just fetch it. You keep fetching it every time you require it. Now assume this is a data that doesn't change that often. All right. So in that case, so let us say my this commerce application, and this is my address. My address don't change that often. So assume that the address is here, or could be any other service. But what would the application do? Instead of querying the database, it would first look for my details in the cache. This is again some in-memory cache service like Memcache or Redis or some other software service, but this is a cache service. Okay, so application would always check the cache for an entry corresponding to my address. If it doesn't find it, then the request goes to the database. The application gets the data, and then the application sends the data also to the cache. Now what happens? The first request was a bit costly for the database and the application, but once the data is fetched, it goes to a cache which keeps my address in memory store. which is much faster than the database fetching my address from the files within the database disk of the database server. So this is much faster. So this is how you introduce the cache. So a term that you should remember always in cache is cache hit and cache miss. What is a cache hit? When an application queries a cache for a particular entity and it finds that in the cache, it's a cache hit. If it doesn't find it, it's a cache miss. If there's a cache miss, the application has to talk to the database, fetch the data, and then populate the cache back. And then going forward, anybody who queries either this application or some other application wouldn't have a cache miss. Instead, they will have a cache hit. The other fundamental building block is queues. So a message queue, or sometimes queue for short, is like a software system that facilitates inter-process communication. Now, inter-process communication, when we talk about, we usually think about the process within a system that communicates to each other, right? But in the case of software design, typically we are talking about a software system to which multiple applications can talk to, and that queue facilitates the communication between them. So what is the advantage of queues instead of these services talking to each other directly? The most important part is it implements an asynchronous communication between two or more software components. So let us say there's a process that produces a message, right? It's in the world of queues, it is called a producer, and then there's a process that consumes the message, which is called a consumer. So this consumer and producer are also usually called publisher or subscriber. And because of that, the queues are also called pub subsystem. So you will hear these names interchangeably: queues, message queues, pub subsystems, etc. So but the fundamental idea is it enables two or more parties to communicate asynchronously. Somebody puts a message in the queue, someone else comes along after 5 minutes, 10 minutes, or even one day and picks up that message from the queue and processes it. And that is the fundamental idea of a queue. So there is no blocking code. Blocking means the first service asks the second service for a message and waits for the first service to fetch a message and then process it. That doesn't happen in a queue. That whole synchronous or blocking code is avoided, which improves the efficiency in a system. So again, this is the picture representation of the queue. A producer produces a message, and and that message is kept in the queue, and one or more consumers consumes at their convenience. So these are the building blocks that we had to talk about. And now we are talking about some of this is not all. There are a bunch of strategies and principles that are part of the system design. But in the interest of time, we would only be looking at some of them. So scaling, we talked about scaling, right? How you enable a system to accept more requests. So there are two types of scaling usually, vertically and horizontally. When you say vertical scaling, you are essentially saying this computer needs more RAM, more memory, or you upscale it, beef up the capacity of the system by adding more memory, adding more faster network cards, etc., etc. Right? So that is called vertical scaling. So a lot of RDBMS servers are they don't like too many systems added to their cluster. So what happens is instead we scale them with to make the single machine more performant. Horizontal scaling means we don't look for improving the capacity of the machine. Instead we add more machines of the same sort and make them a cluster. So that is called horizontal scaling, and that is in system design, horizontal scaling is always preferred. But there are situations where you cannot do it, and you have to vertically scale. But vertical is always about increasing the capacity of a single machine by adding extra hardware. Horizontal scaling is about adding similar machines, more similar machines, so that the scaling is much better and it's cheaper and it's easier to accomplish. Then we talked about availability, right? High availability. So there are typically two strategies for high availability. Let us consider the case of a simple MySQL RDBMS database. Excuse me. So assume that there is a single MySQL server. What happens if that server goes down? Your entire system depends on that database, right? So you need to have high availability for this system. For that, there is another way. The one way is you have to replicate all the data that is in the this MySQL server into another server, and that server should also be able to serve the request. Now, this can be done in two ways. The replication always happens irrespective of whether it's active-active or active-passive. But in active-active, both servers are either taking the request at the same time or they are ready to take the request at the same time. So this is active-active. In the other case, one server always takes the request, and if it goes down, the passive one takes over and start serving the request. So that is active passive. So these are two high availability strategies. A term that you would encounter always is DR or disaster recovery. Disaster recovery is a case where let's say there's one data center or one cloud region where you have all your infrastructure set up. You have designed the system well, you have all the HA availability, everything taken care of. But what if a calamity happens and that whole system shut down, not because of your mistake or your design issue, but rather unforeseen circumstances like a storm, your data center is flooded, or the whole network cable for data center is cut off. Anything of that sort means your system is isolated and it cannot serve your customer. In this case, you need a disaster recovery site, a different data center or a cloud region or something else from where you can serve your customers. That is called DR or disaster recovery. Porting and streaming are ways in which you can have real-time communications. Research about CAP theorem, I'm not going to explain in the interest of time, but CAP theorem, eventual consistency, linear relation are part of distributed systems. And when you learn about distributed systems, you will learn about these things. So, but remember these terms and do research about them. So now let us actually talk about the system design interview, right? So how do you approach a system design interview? So irrespective of whether it's an interview or even if it's an interview, treat it like an actual real life design. You are given a problem and your career or your work depends on it, right? So if you remember the SDS, again, requirement gathering and analysis is the first part. And that is where everything begins. So when you are given a problem or a question, that is just the tip of the iceberg. You get a problem, let's say a simple statement as design YouTube could be your question, right? But you need to understand the problem statement and what is the end goal. Now you and I both know about what is YouTube, but when you are actually designing a system, that is not good enough. You should actually in black and white lay down what is the end result. What should this YouTube do? Do you want it to display ads, or do you just want it to stream, or do you want the people to have the facility to upload videos and see their videos or others' videos? What is it? Do you need all of these features, or do you need a subset of these features, right? So clarify any doubts. So this is very, very vital in a system design interview. Keep asking questions. There is no negative marks for asking questions. Every interviewer will be happy to take any valid question from you. And this is how you get a clarity in the initial phase. Okay. So again, clarify about if the system has some limitations or restrictions that they want to impose. Sometimes people would give you an open-ended problem, but then they would say you cannot do X and you cannot do Y, or you definitely have to do Z, right? So those kind of limitations could be there. So get clarity on all of those. Ask as many questions as you need. So once you're clear about the problem and the end goal, what you have to deliver, right? Then you need to start scoping the solution. So what is scoping? So when we talk about feature or requirements that you got, that is perfectly fine. But then you need to talk about, okay, I'm going to implement the system. These are the fundamental features that I'm going to provide. That's part of the minimum viable product. Sometimes you might have heard that term, minimum viable product, or minimum required features that you have to provide for the system, right? And if there's a limitation, now the interviewer might have given you a limitation. Even if they haven't given you, you could say that, okay, I'm going to design the YouTube, but I cannot design the ad system because there is a limitation of time. But instead of saying I cannot design, you could say it might be out of the scope of the time, so we will park it towards the end. If we have time, we can talk about it. So that is how you scope it, right? Once you have the scope, just don't play it in your head. Make sure you communicate it clearly back to your interviewer. This communication, back and forth communication, is very important in system design, right? You both have to be on the same page about your design. And once you have that, come up with a high-level diagram of the important components in the system and how they are related. So this doesn't have to be very technology-oriented or anything. Just have a few columns, boxes drawn, which are an abstract grouping. These are my web servers. These are my DB servers. That is where you start. It's not your end goal. This is where you start. So it's okay to have very abstract drawings. Okay. Now, once you have that abstract design, right, start breaking down each of these components, high-level components, into smaller components where you talk about actual technologies. So even if you are talking about, let's say, your web server as a group, now when you start breaking down, there's a load balancer. There are different set of web servers. One set of web servers would actually do your video processing, and there would actually stream the video. So there could be like a bunch of different servers. All of these were initially in your one group of web stack. Now they are individual components. That is how you break down the whole things. And then you need to put all those pieces together, how the traffic will go. You need to draw down all those application traffic flow. So at this point, right, you will have a low-level diagram with all the components derived from this high-level diagram, right? Now that you have this whole system, start picking each component and look at where all these systems could fail. You have added an RDBMS. Now, how do you know that this is fault tolerant, right? Whether this is a set. Introduce a slave. So what we were talking about active, or an active passive, right? So in active passive mode, the application of a database is called a secondary system that you add is called a slave. So you could have like master slave MySQL system, or like any RDBMS system. So that is the way like you will look at failure scenarios and introduce high availability and fault tolerance, right? And once you have all those, then you look at bottlenecks. What could, even if I have all these systems, this doesn't fail. But what if I have like 10,000 10,000 requests coming at like at one point? How do I deal with it? Is there a performance issue? Is there a capacity issue? And if you can speculate something, again, this is a hypothetical system, right? You cannot think about the real time request versus how your system would behave in a full way. But you could still make some speculations and add or redesign some of the traffic flows, how you want the traffic to be. This is where you introduce things like caches and additional stuff, right? So that is possible. So again, once you have done all these things, think about the usability from the customer's perspective. That's one thing you can do, right? Your system is well and fantastic, but how is your customer access this system? You are going to be in North America and your customer is going to sit in Bangalore or in another remote corner of India. Is that going to work? Or should you move your infrastructure somewhere else? Or should you have a secondary site somewhere in Bangalore or Delhi, right? So think about that from the customer's perspective. Also, if you have time, think about maintainability of the system, because once you design the system, this has to run, right? If it has to run, you need to know about what kind of things could fail in your system. How is your business going? You are building a system for some business, right? So what is the kind of business metric your application should show? This kind of things, right? And once all these things are done, think about DR strategies. If you need an additional data center for your DR strategy, you have your primary data center in Mumbai, and Mumbai is known for floods. What happens if your data center floods? You need something else somewhere else, probably in India or outside of India. So these are think about all these strategies. It all depends on your time and again your requirements. And of course, in each of these stages, you can and you should talk to your interviewer and clarify. Okay, I'm going to do this next. Is it something that is required? And or if they have some advice or guidance for you. So get that clarity and keep moving through this list. So now I talked about having the high level diagram and all those stuff, right? So if you should be able to do this, but in case you are stuck, right, when you are in doubt, this is what you have to do. Follow the traffic from your client to your systems, and within your system, how it flows through your system, what happens, right? And back to the customer. So that will give you okay, my request comes from the customer, it lands on a load balancer, it goes to a proxy, it goes to an application server, it then moves to another application server, or it goes to an RDBMS, etc., etc. So just tracing that steps would give you a fundamental idea. Once you are done with that, look at the data. What kind of data is each of the requests brings in? What am I serving to my customer? What is my customer bringing to my site? All these contents, where do I store it? Do I transform this data? Follow that data stream. Look at where it is stored, where it is processed. That gives you an additional leverage and additional raw material for building your system, right? So at this point you will be able to start off. And once you start off, once you employ this methodologies, you will have a decent diagram, right? So if you have worries about scaling or understanding the scaling, just start by looking at put all these things that you want into a single machine. Then look at, okay, I have a database here, I have a web server here, my application runs here, my cache runs here, etc., etc. And now how do I expand it? What happens? My disk block is filled up. So you add an additional storage. What if my application is not performing well? I'm introducing a cache in a different server. So this is how you can expand from that single machine also. So these are different strategies you can help that can help in improving your thought process, right? So use them wisely, practice with them. That is how you go. Now that we have laid out all excuse me, all this process, let us look at let us try to solve a design challenge. So what is the question here? We all are users of Stack Overflow. If the Stack Overflow goes down, like definitely our productivity is going to go down. So I'm sure all of you are familiar with this one. So look at something similar to to be built. So this is a simple. I chose this simple system because of in the interest of time. So, but let us just look at what is the requirement analysis and clarification that is required. So a requirement would be always that global user base. This system would have users from across the world, right? And you have definitely free users. All of us are free users, right? And we like to get stuff for free, but you need a business model. Should you have paid customers, or instead should I display ads? So these are kind of things that you can think about. Again, clarify them with if you are in doubt, clarify them with your interviewer and scope your requirements. So let's say look at some minimum features for this service, right? So you definitely require user sign up. User has to log in, and his profile has to be managed. He should be able to manage his details, right? And definitely the primary requirement is asking questions, answering questions, and then of course search questions, right? And of course when you search questions, ultimately you land on a thread of question and answers, right? So right now I decided that there is no ads because I don't have in the interest of time, I'm not looking into that. Probably I will revisit if I have time at the end of the interview, right? So look at traffic flow, right? Here in this case it's pretty simple actually. So think about it. The user has different traffic flows. He could sign up, log in, and look at stuff, or he could have post and comments, just looking at the post and comments, or posting stuff, adding comments or answers, and it could also search, right? So this is the simplest traffic flow that could be there. But again, this could be expanded into much bigger scale, more features. How exactly would you search? What kind of searches would be there, right? So this can be expanded. This is again very simplified structure. And let's look at what kind of data could be in this system. So of course the user data, of course your login data has to be in an SQL store. Your password, your fundamental details, your security questions, probably all of them have to be in an SQL store. But there are also going to be other parts of your profile which doesn't necessarily have to be in SQL, and which could be schemaless or have a flexible schema. Let's assume that your profile has the options to add your social media accounts, Facebook, Twitter, GitHub, almost everything, right? Not all of you would populate it, or you might populate one or two of them. So if you were to add a MySQL database or RDBMS database for storing this profile, it would be a waste of storage and schema, and that's not efficient. So instead you could go with JSON files for each of the user profile, which could be a NoSQL document store. Again, questions and answers. So it is essentially a thread, right? Somebody asks a question, you keep answering. There are threads and subthreads. This can be very well represented using a JSON document. So we are again going to use a NoSQL JSON document store. And the next part is search indexes. The search has to happen on all these questions, right? Questions and answers, right? So again, search index is not exactly a direct storage, but rather there are technologies which can be used for building search on given data. So you could use something like a ready-made platform like Elasticsearch. That's one possibility. It will build its own once you feed the data from all these questions, answers, and the NoSQL document store, that can be fed to Elasticsearch, and then that will build your index. Or you could use the technology like Apache Lucene or those technologies which can build indexes for you. So irrespective of that storage that data is there, it would be part of a different system, right? And then again, this is a data that will be in almost all web applications. Static assets, your JavaScripts, your CSS scripts, profile pics, and any images that you have for functioning of your website. All these are static content, right? And remember, if you see a static content, it is the ideal candidate for caching, right? So you could cache all of these services, all of this content, right? Now, high level, again, oversimplified diagram. You have a web tier, you have a user data handling, and you have search. That's about it. But again, this can be expanded further. Even for a high level diagram, this is too high level. It could even it could be split into further smaller pieces depending on how your thought process goes. And this is where the the low level diagram comes into picture, right? So you have a user, the user's request lands on a load balancer. Once you have the load balancer, it distributes the request into a bunch of front-end servers. So all of these are running the same front-end application or applications, and the load balancer distributes the load between them. Now this application is responsible for displaying the UI and everything, but behind the scenes, how the searches happen, how the posts happen, all of these things are done by backend application servers. So request will go from the front end to many places. Let us say let us look at various use cases. I am a user, I'm coming here and posting a question. It has to go to the backend and to be processed, right? So the request comes through here, front end passes the request to the load balancer of the backend. That load balancer essentially distributes the traffic to one of the backend servers, which would add the request to or the query to a NoSQL store. Now that data will be displayed on the front end when somebody searches it, or somebody adds a command to it, right? Also, if I'm signing up, the request goes the same way, but it goes to a database server, right? Now, if somebody is searching, the front end would directly talk to the search service, which would actually be using the NoSQL and has built the index of that service, right? So this is how that flow will go. And then of course there are static, let's say my profile picture. So the profile picture from front end, it directly goes to the file storage. So this is how you are looking at the low level architecture diagram. Now I haven't introduced performance or high availability in this diagram, but let's talk about them here, right? The only high availability that we have introduced here is a load balancer and a server server fleet combo. So this is a typical architecture anywhere. If you have a bunch of servers that is processing data and it takes request, you introduce a load balancer over there, which will scale and make this fault tolerant. Now what happens to your database server? So the database server requires an HA, right? So there is going to be a primary database here, but you can introduce a slave, which will be in active. This server will be in active mode, and that slave will be in a passive mode. And if this server goes down, the data replicated in the slave will be there, so the slave can take over and become the master. That is possible. Now that is one way of doing things. The other way is you add another server as an active mode. This has some caveats on when you are actually introducing two masters which can accept writes for the same set of tables or databases. There are issues with primary key conflicts, etc., which in itself is another topic, but you could do that as well. You could have a master or an active HA scenario. Now let us look at the file storage, right? File storage could be in a lot of ways. You could introduce RAID here, which is the disk storage. If a disk fails, that can be hot swap, remove it and put something back. Nobody notice anything. That is possible. What happens if the server goes down? For storage, that in itself is a huge topic. How you can do storage clustering. You could build service on top of basic disk and build a storage, or you could reuse some open source product which can do this for you. Typically there are open source softwares as well as cloud service which come under the category of object storage, where you can add static assets and content and other stuff. So you could use that, or you could introduce HA by building that whole system on your own. That is possible. NoSQL store, again, NoSQL stores are easier to scale. They have their own, each type of NoSQL store has their own mechanism, but essentially you can define a cluster which will have some of the endpoints would take in some cases some of the endpoints would take write and the rest of them takes reads. In some other cases everything takes reads and writes. There are a whole bunch of ways in which it can be done. Same applies to search. If you are introducing, let's say the most popular search engine search way of open source search platform is using Elasticsearch. Elasticsearch has its own clusters. You could have read replicas. You could have a bunch of servers taking read traffic and another bunch of servers taking write traffic. So you could scale it in that way. Now look at performance, right? Of course, if you remember the caching from the previous slide, you could introduce some in-memory cache like memcache or Redis here. So in that case, what happens when I'm fetching, let's say my stats or how many stars I have and all those stuff for a user, that could be cached here. It doesn't change that often. If you're running a poll, yeah, you could probably have caching for that as well. So there are things like that you can introduce a cache for. And the best candidate for caching, another best candidate is the static assets. So the static assets you can cache either here, or you could introduce a CDN which would sit between this user and this load balancer, and it will cache all the static components, so that this front end doesn't have to talk to this file storage every time there is a profile picture or like some other static content being accessed. So the CDN will take care of that for you. So that is one way of like improving like the caching. So these are like ways to improve. So again, this is a very simplified and very easy architecture. Again, since this is Stack Overflow, you can Google, and there is an article from 2016 which actually talks about the architecture used by Stack Overflow at that time. You could even see the design diagram actually, and you would see that they have made some decisions, like they don't use NoSQL actually. In my design, there is NoSQL, but the actual Stack Overflow people decided that NoSQL was not a good thing for them to handle, or they didn't want that, and instead they went with storing everything in Microsoft SQL servers. So that's a design decision that they took based on their their practical experience and their interest, right? But does that mean that this diagram or this design is wrong? No. So that is the thing about the system designs, right? There is no one single right answer. Of course, there are fundamental principles and software systems that you need to understand, and you cannot violate those principles. But beyond that, the design is entirely up to you. As long as you can justify your design decisions based on efficiency, performance, and the business requirements or your end goal, that is totally fine. My design and your design will be totally different, and both will be same. I mean, correct, right? So don't worry about that, and it's totally fine. Okay, but do research about the Stack Overflow architecture. I couldn't find a recent architecture, but there was one fantastic architecture, blog post from the CEO of Stack Overflow, I guess, which has this whole architecture diagram listed out. So do check that out. The last point, always remember, expect questions about all your design decisions at every point in your design. Your interview will stop you and ask you questions. Why are you picking this load balancer? Why can't you use a proxy? Why are you introducing cache here? Are there enough data for you to cache? Will this data change frequently? What is the point of using cache? Things like that, right? So this is where those fundamental principles and fundamental technologies that I talked about, those knowledge. See, those knowledge are not tied to a single problem. Those are your brick and mortar that builds your foundation. So once you have that, you can answer those kind of questions. So always expect those questions and don't worry about those questions. If you have the fundamentals ready, you won't have a problem answering these questions, right? And of course, system design interviews are vague, by their very nature. They are open-ended. They give you a problem, but they, more than what they say, they will leave a lot of things unsaid. It is for you to figure out what has to be done, and for that you have to ask questions, use your reasoning and logic, right? See, the aim of the interview is to bring out your planning and design skills, right? So unlike a coding interview or a technology dependent interview where you have a defined scope where it says, okay, solve this problem XYZ, build this API, or talk to me about Redis cache or AWS, right? So those are scoped questions with particular objective. System design interviews are not like that. It is open-ended. That is an advantage for you. It's a bit scary, but it's also a very important very interesting thing for you. Why? Because it is supposed to bring out your own skill and your comfort, right? So once you're comfortable with the fundamentals and you have some reasonable exposure and experience about these things, right? It is a conversation between two colleagues, doing a technology talk, right? You bounce ideas with each other, you ask questions, you get clarity, and you keep designing things, and you iterate. Remember that you might have designed something, and at some point you figure out that, okay, shit, the load balancer or the cache that I introduced here is irrelevant. It should have been somewhere else, or it is not required altogether. Feel free to remove it. Just tell your interviewer that this is my reasoning. Initially I thought about it like this, but upon reflection I feel that it is not required. It's totally fine. So there's always going to be iterations for your design, and don't worry about it, right? And once you get past this initial anxiety of attending an interview and the getting that problem, right, is that you will be comfortable with this. So just enjoy this as a technical conversation and get on with that interview. So that's my last slide, and I hope this has given you some foundation and some ideas to work with. Now I know we have overrun the time, but I'm happy to take questions.
Safir, I must tell you, this was absolutely amazing because I lost track of time itself when I was listening to this, and this has been. And to the audience, please, you can put up your questions on the chat. We have one is fault tolerance and partition tolerance is the same.
Not necessarily. I'm not sure. Partition tolerance is essentially about about partitioning of your the whole system, right? Fault tolerance is about pick a system. What happens if that component fails? As in the previous experience, we were talking about, right? MySQL. Your master goes down. What happens? You need to have fault tolerance over there. Partition tolerance is essentially about you have this whole infra, and part of your infra just fails, right? You have introduced your fault tolerance for your MySQL server and your slave, or another bunch of set of servers. Now what happens? A switch in your data center goes down. No, 7 out of your 10 servers goes down, or they are not gone down, but they are in a different network. That is called partitioning, network partitioning. If that happens, what happens? Will they work in isolation, or will something fail? So that is called partition tolerance. They are not the same, but again, read up on the CAP theorem. CAP theorem talks about partition tolerance.
We have one more question from Abhishek Jha. How can we practice these type of problems?
So again, it's an evolution, right? It's a process, and you have to take time. But I gave you some. So the only thing that is lacking here is going to be the actual problem statements, right? So for the problem statement, you don't have to worry too much. So typically, in a coding question or some other interview, you actually have an elaborate question. In the case of system design, you don't have that. What you have is a very simple problem statement. Design YouTube for me. What would you do? You know about YouTube, right? So instead of me asking you that question, ask it to yourself and think about it okay, what would I do? What are the features I'm going to implement? And what would happen to my performance? How would I store the data? So these are questions that you can ask yourself, right? So that is what this methodology is important. Pick a question for yourself, try to solve it. There will be hiccups in the initial design. And again, remember, there's a lot of YouTube videos, lot of articles which talks about system design in the questions, and you can look at all of them. But what I would tell you is, before you visit any of those questions, look at the question, play the video, get the question, pause there, do the design yourself, and look at the solution after that, and figure out what is the drift, what is the difference between your solution and what this experienced people who are talking about this are talking about. Look at where you missed stuff. Did I miss to introduce this technology, or I was completely blind about this particular system or technology or technique that I could have used in my design, right? So that is how you learn. It's an iterative process. But you would irrespective of that, if you're an engineering student, you would have the basic foundational material required for starting your design. So do that first, and problems are easy. There's abundant. Design Uber, design Flipkart. Whereas pick one service that you like and think about the business. First think about the business problem. What am I trying to solve? Then introduce your solutions, right? And then if you have that solution available online, just look at them, see what is the parity, right? That is how you begin. Yeah, any more questions?
Guys, if there is any question you need to ask Safir, it's the time you can. Safir is with us. If there is anything you need to ask us, you can always ask. Or Safir, could they use your social handles and tag you and ask those questions? Could Could they do
Sure.
that?
Sure. Or I would suggest better, like, let us use the Skilldojo platform itself, right?
Yeah.
You are already listed on the event. Post your questions there. We can follow up there. It's easier,
Yeah,
right?
exactly. You can post a question.
The similar platform is I could miss out on things, right? If I'm busy. But if it is Skilldojo, it's always there's always a second eye looking at those questions, right? You could be there, or somebody else would be looking at that, right? So we can
Exactly.
always keep responding and come back to that forum.
Exactly. So I guess Safir, thank you so much for joining in, and this was an absolute pleasure. I myself enjoyed the session very much, and I also lost track of time because I was learning too, and I was able to understand. There were lot of myths that was busted in my head because I went through books myself. I went through videos myself, so that were very raw, and I felt that didn't give me the specific refinement I needed as per what my requirement is or what I'm learning right now. So thank you so much, Safir, for coming in. Like I said, it's truly a pleasure to have you, and to the audience as well. Thank you so much for joining in. And you can hit the subscribe button that would be, I guess, over there, and you can hit the bell icon too. So whenever we release a new video, you will be able to see that, and it's going to be tech itself. So thank you so much for joining in, guys. Thank you so much, Safir, for coming in. Yeah, absolute pleasure as always. And see you in the next webinar, guys. So yeah, we have a next webinar coming up, and you know who's taking that. Actually, I'm taking that. We have a JavaScript webinar coming at 8 p.m. So yeah, stay stoked. Right? See you.
Yes. Bye bye.